Okay, example 2, a particle moves along the curve y equals the 4th root of x squared minus 3. As it reaches the point 2, 1, the y-coordinate is increasing at a rate of 4 centimeters per second. How fast is the x-coordinate changing in that instance? All right, so imagine we have this graph, and see x squared minus 3, obviously 2, 1 is a point, right? And a 4th root is going to kind of do something like that. I don't know. It's not specific like that, but it's going to be something like that. And of course the graph probably started back here somewhere. All right, and it's saying at the moment it reaches this point 2, 1, this is the point 2, 1, the y-coordinate's changing at 4 centimeters per second. So what I want you to understand is the wording of these problems, what that relates to in terms of x or y or dx over dt or dy over dt. Okay, so let me just real quick write down a few things I know for a fact. I know x equals 2 and y equals 1. Why do I know that?
That's
Points at 2, 1.
yeah.
Points at 2, 1. All right. Is x always 2 and y always 1? No, they're changing, right? This particle's moving along this curve, so it's changing. But at the moment, as it reaches the point 2, 1, at that exact moment in time, that's when we care about, okay? But for the most part, x and y are variables, but at the moment we care about x equals 2, y equals 1. Once you've established some variables, and you might also establish some speeds, always establish speeds as dx or dy over dt, dz over dt to get a third variable. Typically x, y, and z are the variables I use. I guess if it involves like area, volume, stuff like that, I might use the letters involving their dimensions. But dx over dt, dy over dt. Now, look for key words in this to establish sign, because sometimes rates are positive or sometimes they're negative. If something's going in a positive direction, it's going to have a positive speed, a negative direction, a negative speed. All right. And here's what a negative speed would be. If you got a car, let's say a car is here, and this right here represents the distance the car is, right? And the car is going that way, that's a negative speed, because the distance is getting shorter. All right. Is the distance getting bigger or shorter based on their speed? In this case, it says increasing at a rate of 4 centimeters per second, specifically the y-coordinate. All right. So the y-coordinate is increasing. This is the speed of the y-coordinate is a positive 4 centimeters per second. Okay. The number is important. The sign is also important. On every single problem, you have to establish what sign should it be, plus or minus. And if they use words like increasing or decreasing, it's very obvious. As we continue in this chapter, you'll be drawing pictures that represent what's happening, and things will either be getting smaller or bigger. That establishes increasing or decreasing speed. Right? How fast is the x-coordinate changing in that instance? How fast the x-coordinate is changing is just words representing what dx over dt is. So I want you to recognize what we have here. And again, this is where we need to get to every single time. I have my variables that I'm going to be using in my problem, x and y specifically. I got an equation that relates x and y, given to me. That's not always given to you. Sometimes you have to create that equation. But there's an equation relating the variables that you're using. You know at least, well, all but one of the speeds. That's where you need to be. Okay, this represents where you need to be in every single problem. I know all but one speed, I know all the variables values, and I know an equation relating the variables. Once you get to that point, every problem is just like example 1 was. Differentiate with respect to t, substitute everything in you know, solve for what you're looking for. So, the equation y equals the 4th root of x squared minus 3, of course, would be better written as x squared minus 3 to the 1/4 power, because radicals do not differentiate easily. Fractional powers do. We have to establish structure of the equation to establish what type of differentiation is required to differentiate this thing. Y is just a letter, right? Its derivative is 1, easy. X squared minus 3 to the 4th power is a object raised to a power, so this is a product rule on the surface, but then we have x squared minus 3, so a chain rule in addition to that. All right, so if I'm looking at these in pieces, let me do y first, because that's really easy. The derivative of y is 1. Y is not t, so I've got to put a dy dt on it. X squared minus 3 being raised to the 4th power. The derivative of anything to the 1/4 power is 1/4 times that same thing to the negative 3/4 power, right? That's just how you differentiate a power structure. In this case, the power structure happens to have an expression that is not just x inside. So then we're required to differentiate the derivative of x squared minus 3, which is 2x. And all together, once I've done all the chaining and I'm done doing the chain rule, so I did the product rule to begin with, chain rule to finish out the derivative. Once I've established all that, now I'm going to put the dx or dy over dt at that point. Okay? I don't need one here and here. So the power rule is just what it is. The derivative of the inside is 2x. This is x, not t, so dx over dt is required to be written next to it. And that is the derivative of the relating equation. And notice the pieces of that. We have a dy over dt, we got a couple x's, we have a dx over dt. The only thing I don't know is dx over dt, so I substitute everything I know in. You may want to beautify this up a little bit before you do that. It's up to you, your decision. I don't care. Doesn't matter one way or the other. Put in all the numbers now and then solve it, or you put in a simpler version first and then put the numbers in, whatever you feel more comfortable with. Let's just assume we're more comfortable simplifying first. So all together, 2x is on top. Well, actually, this 2 cancels that 4 down to a 2, right? So let's go x is on top, and 2 and x squared minus 3 to the 3/4 is on the bottom. And times dx over dt actually puts dx over dt on top. We get really technical about it. And treat dx over dt just as a variable, so it's a fractional structure, but I don't have to fix the fraction inside a fraction up to that. I mean, that's simple enough to actually start solving this thing. So I substitute everything I know in. Dy over dt equals 4. So this side becomes 4. Equals x is 2. Dx over dt, I don't know what that is. On the bottom, 2 is 2. And then x squared, which would be 4 minus 3 would be 1, right? To the 3/4 power. All right. Simplifying again, 1 to the 3/4 power equals 1. Times 1 doesn't do anything. 2 divided by 2 equals 1. So basically, I end up with 4 is equal to dx over dt. But I ended up with dx over dt over something equals, I'd have to multiply. If I had number times dx over dt, I'd have to divide. All right, just basic algebra at that point. Positive 4. Now, they did give us context this time. They told us the unit of speed this time, so I would expect the proper unit of speed being on your answer. So when you finish this out, dx over dt is equal to 4 centimeters per second. It is a coincidence they were the same this time. They aren't always. Very seldom are they actually the same. So expect them to be different most of the time. This was, again, coincidence. It came out at the same